Okay, we're going to use the residue theorem to compute an integral here, where C, that's our contour, is a positively oriented simple closed curve that contains both 0 and 1 in its interior. And our integrand is the sine of 1 over z over 1 minus z. So this function has isolated singularities at 0 because of the 1 over z, and because 1 minus z is in the denominator here, also at 1. So we have isolated singularities in the interior of our positively oriented simple closed curve. So the residue theorem says if we're trying to calculate the integral of a function which is analytic except for at isolated singularities, then that integral is equal to, over a positively oriented simple closed contour, just as we have in the problem. And that integral is equal to 2 pi I times the sum of the residues. So at each singularity, in our case both of these, we have to create a Laurent series for our function, and then the residue is the coefficient of 1 over z minus zj, where zj is the singularity. In our case, zj will either be 0 or 1. So we're going to have two residues, one at 0 and one at 1. We're going to add the residues together and then multiply by 2 pi I. So first let's talk about the residue at 0. So we'll just call this whole function here f. So the residue of f at 0 is equal to the coefficient of 1 over z, 1 over z minus 0, the coefficient of 1 over z in the Laurent series for this function. So to make the Laurent series, we should remind ourselves that sine z is equal to z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7 over 7 factorial, etc., which means that sine of 1 over z, it's going to put all these z's in the denominator, it's going to be 1 over z minus 1 over 3 factorial times z cubed plus 1 over 5 factorial times z to the 5th minus 1 over 7 factorial times z to the 7th, etc. And now we want to multiply that by 1 over 1 minus z. So 1 over 1 minus z, that one is analytic at 0, and it has a Maclaurin series. This is the geometric series sum, so the Maclaurin series will be the geometric series 1 plus z squared plus z cubed, etc. So we have to multiply these two together. So f of z is equal to this geometric series times this series for the sine of 1 over z. 1 over z minus 1 over 3 factorial z cubed plus 1 over 5 factorial z to the 5th, etc. And we don't need to know the total product here. We don't have to find all the terms. We just want the coefficient of 1 over z. So which products here will give us 1 over z's? 1 times 1 over z will give us a 1 over z. Z times none of these will give us a 1 over z. So let's just ignore that. Z squared times 1 over z cubed will give us a 1 over z. So we're going to get minus 1 over 3 factorial z. Z cubed times any of these will not give us a 1 over z. Z to the fourth, the next term here, z to the fourth, times a 1 over z to the fifth, that will give us a 1 over z. So we're going to get a plus 1 over 5 factorial z. And then there's the other term, and this is going to continue forever. The next one's going to be a minus, plus other terms that don't have a z on the bottom. They'll either have z to higher powers on the bottom, or the z's will be on the top. So our residue of f at 0 is the coefficient of 1 over z, which is itself an infinite series, 1 minus 1 over 3 factorial, plus 1 over 5 factorial, minus 1 over 7 factorial would be next, etc. So what does this series equal? Well, that series reminds me of this series here for sine z, except it has z equal to 1. Instead of having z's here, they're all 1s. Z to the 7th, if z was 1, 1 to the 7th is 1. So it looks like this is the sine of 1. So our answer so far, it's 2 pi I times the residue at 0 is the sine of 1, and then plus, now we need the residue at 1. Now we need the residue at 1. And the residue at 1 is going to be a little bit simpler because the numerator function here is analytic at 1 and has a so it has a Maclaurin series centered at 1. So our function sine of 1 over z, when we have the center at 1, this function's analytic at 1. It has a Maclaurin series, c0 plus c1z plus c2z squared, etc. And then the other function was 1 over 1 minus z, which is just negative 1 over z minus 1. So this is its own Laurent series. And we have to multiply these two together. So sine of 1 over z over 1 minus z is equal to negative c0 over z minus 1. I made a small mistake here. Maybe it's a big mistake. These should not be z's. We're looking for the Maclaurin. I called it Maclaurin series. Okay, that was a mistake. It has a Taylor series. Maclaurin series is only centered at 0. We're talking about the residue at z0 equals 1. So a Taylor series for this function centered at 1 will look like c0 plus c1 times z minus 1 plus c2 times z minus 1 squared, etc. Not Maclaurin at all, but Taylor, centered at 1. So sine, again, sine of 1 over z is analytic at 1. So it has a Taylor series expansion at z equals 1. And it'll look like this. Okay, so sine of 1 over z divided by 1 minus z, and I'll write 1 minus z like this. So then we have minus c1, and if I multiply this times this term, the z minus 1's cancel, and it's just negative c1. And then multiply these two. I'm distributing this across this series. So we're going to get minus c2 times z minus 1, and then minus c3 times z minus 1 squared, etc. And so we can see that the residue at 1 is the coefficient here of 1 over z minus 1. It's negative c0, where c0 is the constant term in our Taylor series. So in general, in this Taylor series, the nth term is the nth derivative of our sine of 1 over z function at 1 divided by n factorial. So c0 is just f of 1 divided by 0 factorial. So it's just f of 1, and our function is the sine of 1 over z. If we plug 1 in there, then this is the sine of 1. And we have this negative sign here. So C0 is the sine of 1. It's the sine of 1 over 1. Z equals 1. Okay, so this gives us our second residue. It's negative sine of 1. And so our integral is equal to 2 pi I times the sum of the residues. The first residue was the sine of 1. The second residue is negative 1 times the sine of 1. And when we add these two numbers in the brackets, we get 0. So this integral is equal to 0. The residues were negatives of one another. So when we add them, they cancel out. And this complicated integrand over this circle, or just some simple closed curve that has two singularities in its interior, gives us a value of 0.